Okay, this is the 6-7 notes for Precalculus 2. In the last section, you had an intro to pretty much everything you need to know about vectors. But there are a couple other topics that are associated with vectors that are very important, and they revolve around an operation called the dot product. So just note that this is not multiplication. It sounds like it is because of the word product, but it is not. The dot product is one of the unique operations on vectors that will actually result in a scalar or real number result or value. Whereas if you did any other operation like vector addition or scalar multiplication, you end up with a vector again. So it's a unique kind of concept, but what we're going to start with is just the definition of the dot product. So let's say that you're given that one vector is a1i b1 plus b1j, and another vector w is a2i plus b2j. If we want to find the dot product, which is represented by v dot w, again, not multiplication, but v dot w is defined as follows. It's a very simple operation in which you take the product of your two A components and the product of the two B components and you add them together. For now, you're not going to know in the beginning here what that actually, how important it is and why it's important, but it will be very soon as a very useful computation for determining a couple vector-related concepts. But before we get there, let's just learn how to use the dot product. So for number one, suppose that you have two vectors. You have v, which is 7i minus 4j, and you have w, which is 2i minus j. So for letter A, they ask you for v dot w. Well, if you look at this scenario, clearly we know that this is a1 and this is b1, and we know that this is a2 and this is b2. So what I mean by those variables is those are the numbers that are in front of the variables I and j in the scenario. So like a1 is 7, b1 is -4, a2 is 2, and b2 is -1. So what we need to do is we need to follow the formula. So just a reminder, so v dot w is equal to a1, a2 plus b1, b2. So if we substitute in these values, we're going to get 7 times 2 plus -4 times -1. So we're going to get 14 plus 4, which is going to give us 18 as the dot product of this vector. So for now, you don't know what that means per se or what it could entail, but for now, just learn the operations and how to use them. What about letter B? So this time, they want you to take the dot product of w with itself. So if we just isolate to w only, just w, right here, then we would be taking the a1 would be 2 and the a2 would be 2. It's because we're taking the same two vectors. Plus the b1 would be -1 and the b2 would be -1. So we would end up with 4 plus 1, which is just 5. Okay, some variations of what you would see. So this is a lot like an order of operations thing. So if you do 2v dot w, then the most ideal thing to do would be to find 2v first. So what does 2v look like? Well, 2v is the equivalent of multiplying each one of the pieces of the vector by 2. You learned that already. So that's going to be 14i times 8j. So then what do they want you to do? They want you to take that vector and do the dot product with w up here. So in that scenario, so let's go this way, our a1 would be 14, which is right here. Our a2 would again be 2. We would add our b1 in that scenario would be right here and be -8. And our b2 is once again our -1, which is sitting right here. So we are going to end up with 28 plus 8, which is 36. Okay, let's do one more. So we have w dot v times w. Okay, so this is why I did this on purpose. I wanted to make sure you don't get confused by multiplication versus the dot product. So just realize that in this problem, we don't want to multiply w times anything over here right now. Ideally, we don't want to do that because the operations are more about taking care of what's inside the parentheses first. And what's inside the parentheses? The dot product. So we want to do w dot v. And then when we're done, we're going to multiply that by the vector w. So just take note here that we already found v dot w. They want w dot v. So if these are going to be, it'll be interesting to see if these are the same thing or they're different. And then we'll talk about that in a second. So why don't we try that? So if we did w dot v, that means our a1 would be 2. Our a2 would be 7. Plus our b1 would be -1. And our b2 would be -4. Okay, that is going to give us 14 plus 4, which is 18. So look what happened here. I'm going to put a little cloud here. It's not the answer yet. So if you look here, it looks like they create the same result, which means, if you remember just basic math, we talked about these properties. Basic math is the commutative property says a plus b is equal to a plus b. So it looks like the same thing with the dot product. So what do we need to do? We need to take now, this is equal to now the number 18 times w. I don't want to do the dot. Times w. So what does that mean exactly? Well, let's look at 18. What is w? W is 2i minus j. So what did we do over here when we did 18w? So let me just write this a little bit better so it looks like this one. What did we do last time when it was 18w? We would just take literally the same exact vector and we would find whatever 18 times each piece is. 2i minus 18j. So if we do that, we are going to get 36i minus 18j, which is our answer. Now, a very interesting development is that all of these answers were all scalar results or real number results, whereas this is a vector result. So the result of a pure dot product as the end result has to be a number, but if you actually notice that the dot product is actually inside of this, if we're multiplying that by something else after, then we don't know necessarily what the result is going to be. This time it just so happens to be a vector. Okay, so what we're going to be doing here is, so this is sort of a cutoff a little bit here. Okay, so what we're going to be doing is, our goal in terms of using these vectors and the dot product, the part of it is going to be to prove a formula. So we know, for instance, if we have a vector in, let's say, the second quadrant, we know that the direction of that vector is going to be some angle used in the previous section using tangent inverse and the little mini formulas I showed you. But beyond that, wouldn't it be interesting if we had two vectors, let's say here and here? Wouldn't it be interesting to find the angle between those two vectors? Well, that is going to be the scope of what we're going to be embarking on in the next, let's say, several minutes that we go through. So if you look at this picture right here, you'll see that we have two vectors, v here and w here, right? And we're looking for the angle between them. So in order to find that, what I did was I set up a diagram in which I had also the angle, the vector u afterwards, in which we can sort of manipulate and derive a very important formula that we're going to need for the angle between two vectors. Now, to be clear, what we're going to be doing in the next several minutes is not something you have to reproduce on an exam. It's just a very crazy formula that we're going to go through and we're going to derive just because the derivation is actually quite useful. So if you look at this picture as we see it right now, we basically want to find the formula for the three vectors that are in the diagram. Okay, so let's talk about that. So look at vector v. So I'm going to outline it again. So vector v is here. So normally we name a vector if it's positional, i.e. it's coming from the origin, which it is. We usually name the vector using the coordinate that the endpoint reaches, or the terminal point. So this vector is actually going to be a1i plus b1j. Okay, just like it always had been. If it had been 3, 4, you would have called it 3i plus 4j. So what do we do with that? Well, we'll talk about that later. What about w? All right, that's our next one. So w, which is right here, is also positional because it's coming from the origin, and it has an endpoint, which means this one should be a2i plus b2j in terms of our derivation. But what about u? Okay, what about u? So let me get rid of this here so we can go back to it. So if we're looking at u, we're looking at the vector right here, right? Like that. Okay, so if we're looking at that vector, you'll see that the initial point is actually a2, b2, and the terminal point is a1, b1. So if you recall, a while back in the last lesson, whenever we had a vector that wasn't at the origin initially, we were able to create a positional vector that was. And how did we do that? We used the positional vector formula for doing so. What was that? That was simply taking the difference of the components of each one, ij, and then putting a plus sign between it. That was our initial formula long ago. So if we were to do that again, what would we do? We would take our a1 minus our a2, so our terminal first component minus our terminal initial component with an I, plus we're going to take our b1, which is our terminal b component, minus our initial b component times j. So what we end up with is we end up with 3 derivation vectors from these variables. So we're going to use these in order to find out how to determine this angle on the following page. Okay, so what I did was I recreated the same diagram over here so we can keep working on it as we go. And note that while V, W, and U in the diagram over here are telling you what the vector is, the actual length of those vectors are their magnitudes. Now, if you look at the picture, this is an oblique triangle. And we happen to be given the 3 sides of the oblique triangle, which gives us a very clear side, side, side pattern. So if you recall, if we labeled these with their actual lengths, so let's do that. So these would be the lengths, their magnitudes. Whenever you use the law of cosines in a side, side, side pattern, we would first square the side opposite the angle we're trying to find, which is here. We would then set that equal to the sum of the squares of the other 2 lengths, which are here and here, right? Then we would subtract 2 times those same lengths, cosine of the angle theta we're trying to find. So if you look at this real quick, we're looking at a very useful formula for determining this in the long scheme of things. So it actually provides an interesting sort of look at the fact that we have now in these 2 boxes a lot of stuff going on, right? It is crazy. It's one of the only big proofs we do in the class, but I particularly love it because you can actually go through and see where the crazy formula we're going to use soon comes from. Okay, so what I did was I took these formulas over here in this box and I repeated them right here, so we don't have to go back to the previous page for us. So in terms of the notes are there. So let's go back to what we already know. So if we know that this is our vector right here and we want to find its magnitude, how would we do it? Well, we would use the square root of a squared plus b squared. But the a's and the b's in this problem have a subscript of 1. So that means this magnitude is a1 squared plus b1 squared with the square root. So that is already found. So we go to w, same idea. That's going to be a2 squared plus b2 squared. If we go to u, instead of it just being just a single a and a single b, now we have quantities that need to be squared. So the magnitude of u is going to be a1 minus a2 squared plus b1 minus b2 squared. Okay, a lot going on here, I know, but what's interesting about that is now if you look at these formulas here and then this original formula that we came out, look what we have right now. We actually have that v is this, so let's put it there. We actually have that w is this, so let's put it there. And here we have that u is this, so we're going to put it right there in the scope of our problem. Now note though, in each one of these formulas that you see down here, each one of these has a square root on it. So when we substitute it into this variable and it gets squared, what happens to the square root? It actually goes bye-bye. So that means when we plug in these formulas, that's what's going to happen. So right now, what I'm going to do is if you look at the orange setup here, so let me just get rid of the craziness that I put in there. So if I look at the orange value here, so when I take that, let me just put this radical up here so it's not confusing. If I take this and put it right here, the square root will disappear, and I will get simply a1 minus a2 squared plus b1 minus b2 squared. Okay, now let's go to green. If I take v, which is this, and put it right there, the radical will again disappear, and I will get a1 squared plus b1 squared. And finally, if I take this right here, and I put it here, the radical will indeed disappear, and I will end up with, looks like a2 squared plus b2 squared. So if you look at this really quick, right now I have all of this filled in on the left, but I know this is weird right now. I'm going to keep this, which is this part right here. Why am I keeping that? Because that is actually part of the final formula. You would never know that unless you were like a mathematician or somebody deriving this. But for the purposes of what we're doing, we want to keep this part as is because we're going to need it. Alrighty, so the only thing left to do here is algebraically do some manipulation on the left side over here. So just remember that when you take two terms and you square them, a binomial specifically, we're dealing with foiling. So this is the same as this. And if you do first inside last, you get x squared minus xy plus y squared, and you get x squared minus 2xy plus y squared. Okay, so all of these, basically the two quantities over here, and here, are going to end up in the same form as this right here. So I'm just going to sort of write it out. We're going to get a1 squared minus 2 times a1 a2 plus a2 squared, then plus b1 squared minus 2 b1 b2 plus b2 squared, and then I'm going to rewrite what we got going on over here on the right side. And then this crazy term, which doesn't look anything like the others. Okay, but this will help us with our proof in a second. So if you look at this, a very nice result is that if you look at, let's say, a1 squared over here, right there, a1 squared over here, they don't have any like terms on separate sides. So if you subtract a1 squared from both sides, then they cancel out. If you take a2 squared from both sides, they cancel out. b1 squared, b2 squared. So essentially what happens is you end up with just the following information. Negative 2a1a2 minus negative 2b1b2 is equal to just the right-hand side, which is the magnitude cosine theta piece over here. Like that. So if you look at this, there are three terms present in this equation. You got this one, and this one. And all of them are divisible by 2, technically, which means that we can do that. We can divide by 2. Now, if you want to go at the algebraic route, which is better, if we factor out a negative 2 from this side, we're going to get this. I'll rewrite the left or the right. Then we can divide both sides by negative 2, and we end up with the following equation. Actually, I'm not going to even write it, because what we end up with is this right here. Okay, so if you look at this equation, there's something on the left side that should be familiar to you. So if you look at a1, a2 plus b1, b2, and you go all the way back to our initial setup here, look at this. a1, a2 plus b1, 2 is the dot product of v times w, if those are your vectors. In this case, I purposely made them our vectors. If you recall, here are two vectors that we want the angle between. So therefore, we know that this quantity here is equivalent to v dot w. And if that's the case, and we take v dot w and we put it in for the a1, a2 plus b1, b2, look what we end up with. We end up with the following equation. V dot w is equal to the magnitude of v times the magnitude of w times cosine theta. Okay, so this is the alternative formula for the dot product, and we use this to our advantage when we're trying to find the angle between two angles. So just to be clear, I'm going to redraw this. So currently we have a vector, hold on one second, I'll look at it again. Yep. We have a vector v, and we have a vector w, and we're trying to find the angle between them. So just real quick, look at this formula that we have here. Look at what is right here. So with all of that work, we actually found the missing piece of what we're trying to find. So if we have the vector v and the vector w, we can find their magnitudes and we can find their dot product, which means we should be able to find the angle theta between them. Now, how do we do that? Algebraically, we solve for theta. And how does that work? Well, we would divide both of these over here, right? And get this as our quantity. And then we would take the cosine inverse in order to isolate theta, and we would end up with this incredible, finally, magic equation. We'll put crazy colors around it just to show that, which determines the angle between two vectors. So that is going to be the formula that we will be using to find the angle between two vectors. But again, be careful here. What do students always confuse this with? They always confuse it with the direction of the vector. Remember, these are two completely different concepts, so you want to isolate them in your brain when you're learning them. So let's go on and do some examples. All right, so remember the goal is we want to use the equation up here to determine the angle between two vectors. So we're given our first problem where we have a vector 3i minus 2j and a vector negative I plus 4j. They are graphed on here. Why are they graphed? Not because you would be provided this, but because it's an excellent learning tool for students. where you can literally see the angle that you're going to get that's between these two vectors. So when you look at this, you see, all right, well, we got a vector in, looks like the fourth quadrant. We have a vector in the second quadrant, so the angle is going to be what's between them, which is right here. So how do we determine that? Well, we have to use this formula here. Okay, but in order to use this formula, we need three things. We need the dot product of v dot w, and we need the individual magnitudes of our quantity. So basically, we could do this, I mean, the best way to do this, there is no best way to do this, but you can either do all the calculations separately and then just plug it in the formula, or you can do it all at once. So I'm going to leave that up to you and what you want to do. I'm going to put it all in the same equation. It is going to look weird, but I'm going to make it nice and big so that you can really see what's going on there. So just to be clear, we're doing the cosine theta is equal, the angle between, which is this, is equal to the cosine inverse of v dot w over the magnitude of v times the magnitude of w. Note, I didn't put a dot between the magnitudes because I don't want to confuse anybody. Dot in vector world means dot product, not multiplication. I know that can be really confusing, but it is what it is, right? All right, so let's put all this into pieces here. So cosine inverse. So the numerator. I'm going to make a big damn equation here. Dot product here. We first have to do v dot w. So remember, the equation for the dot product is a1, a2 plus b1, b2. Okay, so what are the two a's? That's here and here. So we're going to do 3 times negative 1 plus our b's are here, negative 2 times 4. Okay, that's going to be our numerator. Denominator, we're going to have two separate computations. The first one is going to be, so just as a reminder, if you're doing the magnitude of v, that's going to be the square root of a squared plus b squared. But if we're doing v, then we got to make sure we're using the quantities over here. So what is that going to look like? That's going to be the square root of 3 squared plus negative 2 squared. Okay, and then we're multiplying that by, now we're using the same scenarios but with negative 1 squared and 4 squared. Now, this can be very confusing. Why is it confusing? If you're doing these all at once, for the dot product, you're pairing the two A's and the two B components, but for the magnitude, you're comparing an A with a B and another A with a B. So yes, it's a mouthful just saying, but just be very careful with your math that you're not combining things that don't go with one another. So moving on. So if we have the cosine inverse, next is just the mathematics. So what do we get? So for the dot product, we'll end up with, looks like negative 11. Negative 3 plus negative 8 is negative 11. We will also end up with over here, we're going to get 9 plus 4 is 13, so root 13. Over here, we're going to get 1 plus 16, which is 17. So we get this. So hypothetically, we could put this all in the calculator, but I think it's a lot easier to just get it all to its simplest form. So this is going to be negative 11 again. This is going to be root 221 when we combine the radicals by multiplication. And then if we plug it in the calculator, probably a better time to do so. Remember, it has to be on degree mode when you do so. We're going to get 137.7 degrees technically. And I usually just do one decimal place because we're not using it for anything. So what does that mean? That means that the angle between is 137.7 degrees. Now, an interesting thing here is that you're not going to be given the graph on an exam or a lab or anything like that, or probably even the homework. So you can try sketching this, because when you sketch it, you end up with an approximation of what this angle would be. So when I look at this picture right here, I look at this and go, well, this is an angle that's obtuse. It's not fully 180. So I'm looking for an angle that is comparable to that result, and it turns out that I do get that at 137.7 degrees. So looking at number 3, we have two vectors that appear to be in quadrant 3, and we're looking for the angle that's snug between them on the graph. So we're using the same setup here, but I figured we'd do another example. So what are we looking at? We're looking at the cosine inverse of, well, let's do it all out like this instead of writing the formula. So what does the dot product look like? So the dot product is always going to be taking your two a's, which are -1 and -4, and then adding the product of them, and then adding your two b's, which are -3 and -2. In the denominator, we're going to take each one of the vectors individually. We're going to square each of their components, and we are going to add them inside the radical. Then same thing, we're going to multiply that whole quantity times another radical, which is squaring each of the components and taking their sum. So we end up with this big hodgepodge insanity. So we have to find these values. It looks like the top is going to end up being, looks like 4 and 6 is 10. In the denominator, it looks like we're going to get the square root of 1 and 9 is 10. Over here, 16 and 4 is 20. So we'll get the cosine inverse of 10 over root 200. Now, something interesting happens when you put this in the calculator, something probably unexpected. So obviously, the majority of the time when you do these problems, you're going to get some approximate decimal answer. It turns out that when you sub this into the calculator, you get exactly 45 degrees. So 45 degrees is a very familiar value for you guys. So the question is how on earth did this end up being an even perfect whole number of 45? Well, it turns out that if you simplify this, if you simplify this radical, you're going to get the square root of 100 comes out and becomes 10, leaving root 2. You can cancel out the 10s, get 1 over root 2, and then if you rationalize, you're going to get root 2 over 2. Da-dun-dun-dun. So we know that the cosine inverse of root 2 over 2 is pi over 4, and guess what pi over 4 is? 45 degrees. So is this something that's super important? No, but it's a very it's an interesting answer that you get, that when you look at it go, how did that happen? Well, that's why, because this ended up being a very special angle that I manufactured. So at least we could chat about the different scenarios that could happen. It could end up being a very easy looking problem that we would or easy looking answer that we would actually come into here. Okay, so one of the reasons why you learn the dot product is, of course, to find the angle between vectors, but another reason is sort of very important to advanced math, and it's to determine parallelness and perpendicularity. Okay, so these are two terms that you learned a lot about in geometry and in algebra, specifically using slopes. So you might have done very easy stuff in geometry about, hey, you got two parallel lines, hey, you got perpendicular lines, this is what they do, these are the angles. But in algebra, you learn that slopes can determine parallelness and perpendicularity. Specifically, that parallel lines have the same slope and perpendicular lines have opposite reciprocal slopes. So we now bring it into vector world, which is going to be a little bit of a change, because it's a different sort of branch of math, but it's kind of the same concept of what we're going to be getting at. So let's start here. It says, first we state the two vectors are parallel if the angle between them, hey, look at this, angle between them, we know how to find that. The angle between them is 0 or 180. Okay, so that's interesting. So what I did was I gave you the pictures of what this looks like. So I'm going to start with the right picture because it's easier for students to see. So if you have two vectors, which I'm going to draw, so let's say we have W going in this direction, and we have V going in this direction. If we look at the angle between them, it is a perfect straight angle of 180 degrees. So in vector world, believe it or not, we consider this to be parallel vectors. So this is strange because you guys are used to this being parallel, right? So in vector world, we basically talk about a very different setup, specifically that if two angles have an angle between them of 180 degrees, then they are parallel. Okay, there's one other scenario, though, over here. So let's say that I have a vector W, which is this, that is not a straight line. If I have a vector W, which is all of this, right, from this point, but then I come along and I go, hey, I come along and go, what about if I drew a vector W on top of vector, or vector V on top of vector W? So if you look at this, we literally have two vectors on top of each other, which means there is no angle right here. So therefore theta is actually 0 degrees. So again, if we have an angle between two vectors of 0 degrees, we also consider them to be parallel. So it's kind of a very weird looking setup. It's different from what you're used to. Again, this for parallel. It's different than that. But in vector world, that is the definition of something being parallel. So it makes sense that in a few minutes, we're going to be going through examples where we'll have to determine if the angle between them is 0 or 180 to determine if they're parallel. The other concept is perpendicularity, but alas, in vector world and in advanced math, the word perpendicular has changed. I know students are like, seriously? We have another word for perpendicular? Well, it actually is. So in the world of vectors, we use the word orthogonal in order to represent perpendicularity. And luckily, there is no funky business going on with this one. Instead, literally, if you have two vectors where the angle between them is indeed 90 degrees, we therefore say that they are orthogonal vectors, which means they are perpendicular. So these two concepts are important for what we're doing for a lot of the next page, where we talk about how to determine this in problems and examples. Okay, so it's actually common practice to determine if two vectors are orthogonal. So what could we do in order to determine that? So if I had two vectors, let's say, that looked something like this, and we didn't know what that angle was. We knew it looked close to 90, but we didn't really know. So what could we do? We could make that angle theta, right? And we could go back and we could use... Let me get rid of all the noise. Okay, what we could do is we could go back and use this formula and find the angle. Okay, well, that is an option. It turns out that there is a much easier option, and it actually lies a step towards the original formula that we derived for the alternative formula of the dot product. So just for argument's sake, let's take this formula. We're going to go back down. Let's take this formula, and so this is cosine theta here. And since we know that the angle in theory would be 90 in the setup, let's just put 90 in for theta right here and see what happens. Well, if you remember from our unit circle, at 90 degrees, which is right here, we have a point of 0, 1, and if we find cosine, that's the x-coordinate, which means we are essentially replacing all of this with 0 if the angle would be 90, so 0. But what happens, no matter what v and w are, what happens to this whole quantity? It becomes 0. So what did we just do if we basically just eliminate all this middle stuff here? Look at the two end things with equal signs between them. We just proved that if the angle is 90, the dot product is equal to what? 0, which means we don't even have to go through this process. We just have to prove that the denominator of this, v dot w, is 0. That is an incredible finding and something that's used quite often in advanced mathematics, and I summarize it right here. So it says if two non-zero vectors v and w are orthogonal, if and only if v dot w is equal to 0. Now, if and only if means that it can go in either direction. So if the dot product is 0, then it's orthogonal. If it's orthogonal, then the dot product is 0. So that's what it means, just to be sure. So just realize for this purpose is that that is all we have to do if we're asked for something being orthogonal. Okay, so let's take a peek at an example for number 4. It says, are the vectors 6i minus 3j and I plus 2j orthogonal? Okay, so again, you would not be given this picture, so don't look at this and be like, oh, it's 90, so yeah. We're not doing that. You wouldn't be given the picture. I give the pictures so students understand what they're doing visually, so the math means something. So if you look at this, note they only asked if it's orthogonal. If they only asked that, then all you have to prove is v dot w equal to 0. That's it. That's all you have to do. So if we go down here, we go, well, what is v dot w? We would simply say, all right, well, v, if we're doing our two a's are 6 and 1, right? So we're going to do 6 times 1 plus our two b's are -3 and 2. So we're going to get 6 plus -6, which is, ta-da, 0, which means we would say that these two vectors are indeed orthogonal. Okay, so just to be clear, why does this work mathematically? Because if you went back to the formula that we talked about before, the one I just erased there, if we went back to that formula, what's going to happen is v dot w is going to be 0, which means 0 divided by anything would result in the cosine of inverse of 0. And in this standpoint, if you're looking for the cosine inverse of 0 degrees, then you're going to end up with a 90-degree angle. So how do you know that? Well, you're looking for when the x-coordinate of a coordinate on the plane is 0, and that only occurs at 0, 1, which occurs at 90 degrees. So instead of going through that entire process, we instead just isolate it, because this would happen no matter what scenario you got. v dot w is 0, so we isolate it to this simple formula of the dot product of v and w will always be 0 whenever they are orthogonal. Okay, so we showed that things are orthogonal, or vectors are orthogonal, so what if you're asked to prove that they are parallel? So remember, what we learned before was that in order to prove that two vectors are parallel, we need to know that the angle between them is 0 to 1 or 180. So just FYI, there is no shortcut to this. So with orthogonal, we were able to use this little easy mini formula. There is no shortcut to parallelness. So we need to know if the angle is 0 to 180, which means we have to go right back to using our angle between formula, which I'll rewrite here, v dot w, product of magnitudes in the denominator. Okay, so that's what we're going to do. So let's go ahead and look at how this sets up. By now, you've had a lot of practice with this, so hopefully it's going well. So remember, the dot product is the only scenario where you go vector to vector with the components. So 2 times -6 plus -3 times 9. In the denominator, the magnitudes are when you're isolating each of them. So 2 squared plus -3 squared in the radical times, and then isolating this, -6 squared plus 9 squared in the radical. So what do we get? We get the cosine inverse of, if we do the math on the top, we're going to get -39. In the denominator, we're going to get root, I think it's 13, it looks like. Yep, 9 and 4. And over here we get 81 and 36, which is 117. Okay, note that if you just take the product of these guys right here, you get root 1521, which is going to give you, if you put that in the calculator, you're actually going to get negative 39 over 39, which is negative 1. Okay, there's a good chance that you're just, because you're remote, you're just using your calculator here, which is not ideal for the class, but it is what it is, kind of. Ideally, what you would want to do is work until you got to negative 1 and then look at the unit circle and go, where is the x-coordinate negative 1 on the unit circle? Well, that only exists here at this point on the unit circle, which means what is the angle? 180 degrees. So what did we just prove? We just proved that the angle between these is 180 degrees, which, by the way, means that one is going this way and the other one is going that way. So that means, so 180 degrees, right? So that means that we do have parallel vectors in this problem. Now I just want to do sort of a side note on this. So sometimes, whether you will see that this year in a remote environment or not, sometimes you will be given two vectors and it will ask you whether they are orthogonal, comma, parallel, comma, or neither. Okay, so it'll be one big problem. If you are asked to do that, the best strategy is to always check for orthogonality first. Why? Because the formula is super easy. If it is orthogonal, you're done and you say it is. But if it's not, you move on and you find the angle between them to verify whether it's 0 or 180. If it is, then it's parallel. If it's not, then it's neither. So think of it as like a flow chart. You check for orthogonal first, then you check for parallel next using the bigger formula, and then if neither of these work, then you say that it's neither. That would be the best strategy to use in that type of problem, which does come up. I don't know if it will in a remote environment, but it does come up usually in a non-remote environment in class. Okay, so the last concept in this section is called work. This is also the last concept in the class, so that's pretty neat. So this will be our last live lesson that we'll be doing, or recorded lesson. So the last concept is actually called work. Okay, so just as the definition, the work done by a force F moving on an object from A to B is as follows. So we end up with this little clever formula right here. Don't love it, but basically it's the dot product of the force times the vector. Okay, so what we're going to do is we're first going to do a problem in sort of a very simple version of what this is about. And then we're going to turn it into more of what we've been talking about in terms of the problem. So let's start with just this problem. It says, suppose you're driving along a level road and you're out of gas only 200 feet from the gas station. You decide to push the car in the gas station in neutral. Let's say use a constant force of 90 pounds. Okay, so again, you're at point A over here with the car. You need to get to the gas pump at point B, so you're pushing the car with a force of 90 pounds at a distance of 200 feet. So according to the formula, we would take the work to be the magnitude of the force, which is 90 pounds, times the distance that it must travel from A to B, or the magnitude of the distance, which is 200 feet. If you multiply that, we get 18,000 foot-pounds. I know that's a very weird label, but we are indeed multiplying a pound measure by a foot, and we get 18,000 foot-pounds. This is a very simple version of work, which I like to show so students at least see it. They can see like what is happening when you calculate work. But in reality, the true formula is based on more vector work that we did before. So I want to concentrate on this formula over here. So if you recall, just from this problem, we were on a level surface. So when is that always going to be the case? It isn't. So if there's an actual incline of some kind, then we need some type of theta in our problem to represent that. So if you look at the original formula again, which is this right here, work is equal to F dot AB. So in reality, we treat these two values as vectors in a sense. So v dot w. So if we go to if I'm going to do some traveling here, so I'm going to try to go slow, not to make anybody nauseous. So if we go all the way back to this right here, this alternate formula, look what we got. We have v dot w over here, and we have this over here. We have the magnitude of v, which is the first part of the dot product, the vector. We have the magnitude of the vector w, and then we have cosine theta. It turns out that this helps us in our determination for work. So let me just rewrite that all the way at the bottom here when we get to work. All right, so this is equal to the magnitude of v times the magnitude of w times cosine theta. So look at what we did. So f over here becomes the magnitude of f, which is our v. AB, which is our w, come over here. We take the magnitude of AB to get our magnitude of w, and then just copy cosine theta. So literally, this is the original formula. We've applied it to the work equation and ended up with this fancy little formula for determining any work done on something with an angle, basically, or angle of elevation. So let's look. So number 6, it says a child pulls a sled along a level ground by exerting a force of 30 pounds on a rope, makes an angle of 35 degrees with the horizontal. So real quick before we go anywhere, so you can see there's a person here pulling on a sled, right? There's 30 pounds of force going from the shoulder to the sled, but it's at a 35 degree angle from the horizontal. So the last part is how much work is done pulling the sled 200 feet. So basically we need to go 200 feet in order to get there. So if we look at the work calculation is going to be the magnitude of the force times the magnitude of the distance you must travel times the cosine of theta. Well, the magnitude of the force is given as 30 pounds. Okay. The distance that's traveled, it looks like must be 200 feet. And you're multiplying that times the cosine of the angle that it makes with the ground. So if you put this all together and do the calculation, you're going to get approximately 4,914.9 foot-pounds. Let me just, hold on. Foot-pounds as our value. So let me make this so it's not confusing looking. Approximately 4,914.9 foot-pounds. So this would be the work done on the sled by the person pulling it. So basically, this is a very straightforward concept. It will probably appear in various places. Homework maybe, I don't know if lab maybe, exam could be for sure. So just realize that this is an application of this fancy little alternative dot product formula, but instead we use it on this application called work, and whenever we do an application, of course, we have a decimal. So that would be it.